I think we can get started. Great. So yeah, we're delighted to have Kirill tell us a bit about steering generative models. So please, Kirill, take it away.
Thank you. My name is Kirill Neklyudov. I'm from University of Montreal in Mila, and today I'm gonna give a talk on steering generative models from mathematics to biomolecular design. And the talk is, I decided to go for kind of like a talk with like a very simple, basic concepts, and I'll talk about this like probabilistic kind of set. Probabilistic set operations. So this is kind of like set operations that we want to define with probabilities, and then I'll talk how we apply this to generative models, but very briefly because I don't want to like go into details and like put like lots of partial differential equations in the slides. And finally, I'll talk about applications, and I also try to put kind of like as a red line through the slides, through the presentations, potential applications, what these set operations can be like useful for. And okay, we'll start with the probabilistic set operations, or kind of like weighted set operations. And I'll just list everything that you all know from like basic, like these Venn diagrams from like basic courses on like measure theory, or like, I don't know, like set operations and logic and so on and so forth. So like there is like a full set and the set, and then like negation of set, intersection, set minus, and union. And we'll give all of them kind of like probabilistic meaning that's going to be helpful for us for the generative modeling. And we'll start with the full set. And for the full set, we're going to consider the set of all possible systems, all possible states. And here I suggest to think about like proteins, because we're going to do application for protein generation later. And the set of all possible proteins, of all possible states, we can just describe as like a Boltzmann distribution with like some temperature T capital, some energy E, and it essentially gives a weight or like probability to every state of our space. And this is going to be the full set. We're going to denote it as pi of x, just for convenience, because we're going to use it a lot. And next, we'll go to the definition of a set. Okay, so for the definition of a set, we're going to take the proteins, let's say, that all bind to some ligand A or some other protein A. It doesn't matter, something A. And we'll introduce this as follows. We'll say that this is the conditional distribution x given A, okay? And we're going to multiply the entire set of proteins, pi of x, by this indicator function that tells that this is only the subset that has some property A that binds to A, okay? And now this kind of like, this is our probabilistic set where we define it as the proportional to the product of these two. So this is kind of background density. It's always there. You can think of this. And this has the meaningful kind of part that we're going to play around with. This indicator function, it's simply pi of x if x is inside A, and 0 if it's outside. So in the end, you can see on the picture this kind of circle that like takes out the meaningful part. OK. So now we can introduce the operation. Based on this definition, we can introduce the operation of the intersection of two sets. We can say that, first of all, like intuitively, we understand what it is. We just need to take two circles. We just need to take the probability mass, probability density, in the intersection of these two circles. And for applications, we're going to think of this like all proteins that bind to both A and B. We can go ahead and just write down the definition that like P of x, A intersect B, and this is like, we put this into the definition of our set function. And we have here like the indicator function that we can split in two. So we can split it into the indicator that x belongs to A and the indicator that x belongs to B. So like it's clearly the intersection because this thing is one only when x both belongs to A and B, right? And then we can go ahead and we can split it further. So we can think of pi of x here as the square of the square root of pi of x. And then, of course, square root of the indicator function doesn't change the function. So we can apply this. And finally, we can say that this is the proportional to the square root of these two things. So we arrived kind of like to defining the intersection through some algebraic operations on the set definitions. So this is the first thing that we need. And another thing that we need is the definition of a complement of a set. So this is like all states outside A or not A. And once again, intuitively, it's very easy to intuitively draw these pictures. We just like put like a circle, and then we like blur everything inside the circle, and outside we don't blur. We just weight by the probability. And this is important. This is an important definition because sometimes we want to generate proteins that don't bind to something. It's sometimes bad if proteins like bind to something. So yeah, let's see how this plays out. We start with the definition of a set. We say that a p of x given not A is proportional to pi of x, and then the indicator function that x is not in A, okay? And then I claim that we can put this into the denominator. So pi of x divided by the indicator function that x is inside A. And this is a good moment that if you like raise your eyebrows and say that like, in what sense? Why is it possible? And intuitively, of course, I can tell you that, okay, if we divide by a 0 and it becomes infinity, after the renormalization, the infinity can become like a normal value. But if we don't divide by 0 and we don't get infinity, after renormalization gets very small. So anyways, formally, in what sense? In the sense of the limit. That's the correct reasoning here, and we can first say, okay, let's pretend this thing is correct. Let's put this small epsilon here to make things kind of like normal and not exploding to infinity because we don't want to operate with this. And let's say that like we just added epsilon here, and we also multiply by 1 minus epsilon. So the function is still like if x is inside A, we get 1. But if x is outside A, we get epsilon in the denominator. And of course, I was using these like proportional signs everywhere, just like not caring about the normalization constant. But here, the normalization constant, z epsilon, plays like a major role. So in particular, we can just formally write down its definition as the integral over the entire set omega. And we can we integrate this part, of course. And the integral is super simple because we just have to like consider two cases. When x is inside A, then this is 0, and this is like pi of x divided by epsilon, and this is pi not A. This is if it's like otherwise that's the PA because this is 1 epsilon minus epsilon, blah, 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 and like we get these two terms, okay? So now we put this back into the equation, and we see that we can use this z epsilon, and we can like do some algebra and like rewrite this indicator function, and we get here something, this multiplication by the bracket, which almost looks like indicator function that x is not inside A. And the only step that's left is like we have to take the limit of epsilon goes to 0, and we'll arrive to what we started with. So you can see that this definition of P epsilon x not A is indeed the indicator of x not in A multiplied by pi of x. And in practice, it looks like this. I mean, in practice, I mean the limit, right? So we just take in the limits. You can see visually how it converges to what we want. OK, so far so good. If we are happy with this transition, then we should be also happy with this transition, because this is just the identity. It's multiplying by pi of x to the power of beta, both in numerator and denominator. And that's it. That's the final step, because what's on the slide here, it's the measure of the entire set to the power 1 plus beta. And this is the measure of the A set to the power of beta. Yeah, so we define the complement of a set. Same thing goes for the set difference. And this is the most practical definition, because we can define proteins that bind to A but not to B. And this is important for like safety panels when we generate some drug. Do we take questions in the middle or after? Oh, OK. Yeah.
Quick question. So for the complement, if we use 1 minus indicator instead of A, why wouldn't that be?
Yeah, that's a great question. You can do this. It's just going to be much harder for generative modeling. Yeah, because when we I'll get to this, but once we want to define like operations on probabilistic models, you can think of like energy-based models, for example. You can clearly like add energies or multiply densities and try to sample from it, right? But if you try to subtract things, then you have to like be very sure in your normalization constants, right? So they like cancel out perfectly. So that's why we're working with this. But that's a great question. Thank you so much. Yeah, set difference. Important in practice because we want to generate a drug, and we want the protein to bind to something we want it to bind, but then if it binds to something that we don't want it to bind, then we won't get a drug. We can get like a poison or something. It can mess things around, right? So this is quite important, and this is also quite easy given the previous definitions. We start with the definition of a set, as always. We say that P of x conditioned on A not B, A set minus B, is pi of x by the indicator function, and then we just expand this indicator function as a product of 2. So x should be not in A and not in B, right? And then we apply the same trick from the previous side to the indicator function x not in B, and we put it into the denominator. That's the whole trick. Then we multiply by pi of x to the power of beta identity, and we arrive at the algebraic expression that depends on P of x given A, P of x given B to some powers, divided, multiplied, something like this. So that's the main thing. It's a very simple expression, and in terms only of P of x given A, P of x given B. So in the end, we formalized every single set operation as some algebraic expressions here on the definition of a set. And of course, this is important, as just discussed, because we can now introduce our like energy-based model or some other probabilistic models, and we can actually use the models conditioned on A, conditioned on B, to define the samples conditioned on A set minus B. It means that we don't need yet another special conditioning, special sign in our probabilistic model to use this. I just threw here the union of the set, and the union actually requires pluses and minuses, unfortunately, but doesn't matter. We don't need union for our practical purposes so far. So I'll talk about this. This is literally the next point of the conversation. Why do we need this for, and how do we use it in generative modeling? And I'll start with discussing how do we collect the training data, or how we wish the training data would be collected, probably. So let's say, once again, we generate proteins. It means that we have like a database of sequences with structures. They are like spatial coordinates, right, like of all the atoms. And we have a binding score to something A, ligand A, let's say. And then we have the same for the B. We can like take the same sequences and then like put the binding scores. So this indicator we should think about as a cutoff. We say that like the binding score should be lower than -11 for things to bind properly to A. And we put this kind of everywhere, and that's how we think about this conditional distribution, right? And this pi of x, we can think of this as like frequency of appearance, but in the limits of like a very large data set, we would love this frequency, we would love this density to be like the true energy, right? So the Boltzmann distribution with the energy of like of the system, the potential energy. Okay, so this is the data. I think it's convincing that we can like kind of like collect empirical data from this conditional distributions. Now, what do? I think it's kind of useless to describe on the diffusion model workshop, but let me just go to, let's say, define notation. So we interpolate between some simple distribution like normal distribution and our empirical distribution conditioned on B, or we can write it down as a PDE, right, with some densities, and then we can like reverse this PDE in time, and this is the model that we actually learn. But yeah, once again, I assume like everyone here knows. Let's look at the picture, how it looks like. So we start with the standard normal Gaussian, and we arrive at P of x given B. That's the final state, right? So this is how this interpolation looks like. So training a generative model, in particular a diffusion model or a flow matching, many other models, on this data would allow us to sample from P of x given B by defining this kind of like time-dependent process. Okay. And I suggest we don't think about PDEs here at all, because it's just some accounting that's not very interesting and is not like elucidating anyhow. We'll just think about this like a time-dependent process that changes smoothly marginals from normal to this condition distribution. So now, given like trained model on conditioned on A and trained model conditioned on B, we can do this, of course, through like amortization, as like we can like put labels into the model. Yes?
Why is the shape in B kind of getting this multimodal type structure? Shouldn't restricting to B just be like the same density but renormalized?
Same density but renormalized. Yeah, but the original density is multimodal.
Oh, you're moving from Gaussian. Got it. Yeah, that makes sense.
Yeah, so given this model, conditioned on A, conditioned on B, what we can do is we can multiply these densities, take the square root, and yeah, in the middle, when like we do this for Gaussians, it's just gonna be like the same Gaussian from the beginning, right? In the middle, it's gonna be something weird, but what's important is that like in the end, it's gonna be this intersection of samples that we want to sample from. Okay, and the whole kind of trick is that we know this PD, we know this PD, and how do we find this PD, right? And this PD is defined by these marginals, of course. So now how do we define the sample set difference? Once again, I don't even change this like left side of the slide, right? I just like the processes are already defined, the model is already trained. I don't need to do anything else but to take like a proper algebraic expression, right? Like multiply these existent like densities that I have access to some powers. So multiply, divide doesn't matter, like matter of notation. And once again, we can define this PD. And just to give a taste like what these PDs would look like, and or like what's kind of the seed for the proof of or derivation of these PDs, it's quite straightforward. We just say, okay, I think at this point I convinced you that like all these operations can be expressed as like multiplications to some powers, alpha, beta. Of course, we have to be careful with the normalization constant. And then what we do is like just this is just expanding the derivatives by the rules of the derivatives with the partial derivative over t, and then a little bit more because we have to like expand these things. And we're going to expand them and have here the derivatives inside the integral because we take the derivative of the normalization constant, and so on and so forth. This is like just honestly algebraic exercise. And what's important here is that we start with what we want to find, okay? And these things here, these derivatives, we already have. We already have them from the PDs that we defined for the interpolate, for the diffusion process. We have them in practice, yep.
So just about this so on and so forth. So I wonder whether you just combine eventually the scores function, average them, something like that.
Okay, yeah. That's a great question. I indeed like put like too many details probably here. I'll say like a couple words probably, and we'll move on. So the idea here is that we can try. So okay, the philosophy in here is that we would like to take this partial derivative, plug in our like diffusion Fokker-Planck equation here, okay, everywhere, and see another Fokker-Planck equation, right? That would be cool. Because then it means that like we take the kind of like, we have an algebra on the diffusion processes. That's kind of like, we combine diffusion processes and bum, 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 we get another diffusion process. Unfortunately, that's not true, but almost true. So,
So you want to reconstruct, combine the whole process in T, right?
Yes. The whole process we want to derive the PD for this entire process. Just multiplying marginals of every process, taking the derivative, and see what this PD is. Okay, and this is like it's going to be almost Fokker-Planck equation with some important sampling. That's I think the best description of this. To be precise, it's going to be like these like Feynman-Katz formula with like sequential Monte Carlo tools to sample from it. That's the idea. Yeah. In the end, we have all these processes here defined like now in time, right? We just multiply marginals according to these like formulas, and we know that, yeah, we start in the beginning probably from a Gaussian, in the middle is something like not very interpretable, but in the end, we arrive to what we want. We arrive to like, let's say, set minus formula. And as I said, this is like requires some like Feynman-Katz formulas, and that's why we call it Feynman-Katz correctors in diffusion. This is a paper you can read about details. Yeah, yes.
To power alpha and beta? Like, what does it do?
Oh, that's a great question. So there is no kind of like benefits in here. So we raise to the power of beta as kind of like a trick to find formulas that we've already used before. So in here, this set minus A set minus B, to express it as the densities of x given A, x given B, we have to raise to the power of beta. And actually, it works for different betas, except probably like beta equals 0, something like this.
You get to choose beta however.
Yeah, that's actually quite anti-clickmatic, I would say, in the sense that like you don't get like a single value of beta. It's a parameter that you can like do probably you should like sweep over in practice, get some value, and that's it. Yes.
I was going to ask the same question because you could do the same thing for the intersection, right? Like you just need to have like you could have p t x or beta.
Yes.
And the other one 1 minus beta.
Yes. Yes.
And so, like, have you tried, like, I don't know, like having like a schedule for those things? Like, beta could also depend on t or no?
Yeah, probably, honestly, because in the end, we don't even care what was like in the middle. We care only what's in the end. Yeah. So we can like anneal beta. We can like experiment with this. I think that in practice, this is very, very important because in practice, the formulas we have in the end in these PDEs is like kind of like what you have to do is you have to like take the scores of your two diffusion models and like add them up with these powers of like beta, right? So it's kind of like a classifier-free guidance plus some like resampling and like some shenanigans on top. But we know that like classifier-free guidance has like a kind of like a range of like applications. So this is where you tune the beta but yeah, I agree. That's kind of, I think it's kind of weird that we don't have like a specific answer here.
But I was wondering if you had like any idea, like, I don't know, have one beta that's going to reduce the variance of like, you know, help for the SMC part or, yeah.
I see. So I would say that like in practice, we just do a sweep and like take the best value. Yeah, I think it's I think it's like you should think about this as the role of like guidance in the classifier-free guidance, and then but yeah, I don't have like a better answer, unfortunately. Yeah. All right, so this is the paper, and oops, that's too fast. Yeah, because I wanted to say that the same things work for the discrete case. This is the full distribution, and here we can like take the subsets with the set operations and so on and so forth. The idea here is that like it's just a different differential equation because it's just a jump process, but the idea that I showed here with the derivation, pretty much the same kind of philosophy of derivation works. Just instead of the Fokker-Planck equations that we like substitute here, we should put the corresponding jump processes, and it's gonna work out. And this is called discrete Feynman-Katz correctors. All right, so far so good, and I'll go to the applications. For protein generation, we have to be a little bit more mindful because protein generation requires co-generation. It requires to generate the sequence and the structure, and preferably at the same time. So this is how we can think about it. We can think that this is the joint distribution of the structure and the sequence that bind to like ligand A. And we have these sets defined like by the ligands, and we can do the same operation. So I think we, in the paper, rewrote like literally the sum of two processes and cited like Molly-Tao paper with the co-authors on how to like do like co-generation, and that like essentially co-generation can be considered as like product of two processes. And so it's literally a straightforward continuation of the previous two works. Yes, I would like to talk about some results, and I would like to show that, these are kind of like three cases, approximately in the increasing difficulty from the easy one to the hard one. And this pink bar you can see here, this is no guidance at all. This is like just sampling from the model and trying to see if something kind of sticks. And we want to like bind to, this is A set minus B. So we want to bind to biotin and not PLP. And you can see that like in a lot of cases, just making like a lot of attempts, it's gonna work because it's an easy case, okay? But in some cases, you'll, out of like 1,000 generations, you'll get 0. And this is where the guidance helps. These are kind of like successful attempts in some notion of like binding quality and separation.
These are not experimental results.
No, these are in silico results. Yeah.
And also, how do you do the cogeneration again? Seems like very tricky.
Yeah, so it is tricky, and it is hard to train this stuff. But in general, like you do kind of like two diffusion models together, or with like discrete and continuous, and you generate both like the sequence, unmask the sequence, and you generate the structure, and you like input both states to your next step, and that's kind of the idea. But that's kind of like, there is a lot of details to it. Honestly, it's better to like open this paper and look it up, because that's the whole kind of, that's the main result of this paper, is the cogeneration. And
Do you do multi-flow, or is just one scheduler for both of them?
there are like probably different schedules there, but it's tricky to like align them so that you generate them together. That's yeah. And finally, I would like to talk a little bit about the paper that's going to be soon on arXiv. We called it Select Bench, because we learned in this kind of real problem that it's very, very hard to generate this selectivity. You could see that like I was showing you like 6 successful samples out of like 1,000 attempts or something like this. So that's why we decided to like, given kind of like the experience we got in this paper with the code generation, we decided to make proper metrics in proper like data set cases where people can like try to test their models in the selectivity task. So we want to bind to the on target, and we don't want to bind to the off target. These consist of 3 different cases, benchmarks, kind of like, first is the case-based select bench. It's just from the literature known important cases of like on targets, off targets. Safety benchmark is provided by some regulatory institutions on clinical trials. We can just like a list of known off targets don't bind to this. So it's good to test on this. And then Excel is kind of like, we took a large data set, and then we try to like come up with different examples from there, like binding to on targets and off targets. We tested a bunch of generative models, diffusion and autoregressive, and those who were trained with selectivity in mind, or were those who were like guided with selectivity in mind, different things. And what we can see is that the situation is not very good. So like it's kind of like, it's good that something is generated. So I think it's always positive when we can generate something in silica and don't need to run the experiments. But at the same time, the problem is far from being solved. This is the open problem, and I think it's very interesting, and the community still haven't resolved it in some way. And this is already kind of like unrelated to the previous part of the talk with the like set operations, because who knows what's the best approach in practice in the end. Yeah, it's called On the Selectivity of Generative Models in Structure-Based and Drug Design. And that's the final paper. I wanted to say that the most valuable players of this works was my postdoc, Marta Skrata. She was supposed to give this talk, but she couldn't come. And I'm a substitute for her. Yeah, and I'm happy to take more questions. Thank you. Maybe all the questions were addressed. Yes?
I have a quick question.
Yeah.
Why can one not do union with, like, let's say, complement, A complement, intersection, B complement, maybe?
Yeah, that's complement A. So I'm sure there are like more ways than I wrote. And maybe you're right. I was just kind of going for the inclusion-exclusion formula. So A plus B minus intersection, because it felt very general to me that I can like.
But then there's the addition, right?
Yeah, exactly. No, the addition is bad. So honestly, I didn't put like enough kind of like brain cycles into the union because we never used it in practice. We're mostly using like set minus. I think it's interesting. I think I went for the inclusion-exclusion formula because it's general in the number of sets. But I think there's another, the fact that we can like write down these identities, it would be interesting to see what's like best in practice and if they're like consistent kind of like. I think that's a good suggestion on like different ways to write down the same notion. Yeah. Yeah.
I had a philosophical question on the issue of the cogeneration. Why do you think we should do cogeneration? I mean, in principle, a structure is everything.
Oh, no.
I can just generate the structure and just get the sequence out.
Yeah,
and
yeah.
I don't have to, because it's very tricky, because the sequence may dictate the structure too early, and that's what we have observed in our group.
I agree completely. And I think this project was like, in part, like an exploratory project in this question. So see if we can like reap any benefits from the code generation. The motivation might be that exactly what you said, like sequence guides the structure, and we want to like do some like reward on top of the structure, or maybe we want to do the reward on top of the sequence. That's why it felt kind of like an interesting question to study. But I think that it's not, the paper doesn't suggest that this is the only right way to like do generation. And I agree with you completely that like, I mean, we're doing like autoregressive models, right? Like so many, we mathematically, we just write down the like conditional distribution and like it all somehow works. So yeah, I agree completely. You had the question.
Yeah, I was just curious what your thoughts were on like the main barriers for doing better on this like selectivity benchmarks. Like, do you think this will just get better with the sort of underlying generative models getting better, and then just using this guidance framework that you already have, or do you think it requires like more work on just how to even do the guidance better?
Yeah, I mean,
generative models, or is it really open?
Yeah, that's a great question. Thank you. I would say that the framework I presented is kind of the naive version of this would be just to collect a data set with all the possible intersections, unions, and train the model, right, with the correct conditioning on the intersection, on the union, and like all the possible sets. We thought that that's kind of the not scalable approach, because if you have more and more conditions on like on targets, off targets, your simply labeled training data is get like super scarce, right? And that's why we want to like hope for the generalization. I think the generalization, that's my intuition kind of, is the main hope here. And of course, it's going to get better only with like better pre-trained models. And then the guidance is like a thing on the top that we kind of put in and try to do. But I think in practice, it's always, you know, like when you set a, like some baseline, it's going to be a mass of things, you know, like it's going to be a bunch of tricks. It's not going to be like one neat solution. So I think we do need better pre-trained models on larger data. Maybe we need to start putting like intersections and like selectivity during pre-training or like fine-tuning, something like this. And then the guidance on top, just, you know, like to throw your like hat in the last mile to say that like this is where as far as we can go. So that's my intuition. So I think it's kind of like a layered thing. Yeah. Yeah.
So, you know, when you do something I've been curious about, when you do the Feynman K correction and then you have like, okay, you do the SMC because like the guidance is not like just adding the two terms. If, let's say, I don't want to use the SMC part and I know it's not correct,
Yeah.
do you know what kind of like, what is the failure mode that you see in that case? Like how far are you from, you know, because it's, if I can not use SMC, I prefer not to use SMC.
Yeah. That's kind of like hits in the heart of this approach. Yes, because as I said, like once we write down these PDs, we have to do resampling. I think the failure mode is most of the time is kind of mode collapse. That's the classical thing for SMC. We do though observe that like even when it mode collapses, the quality in the end is better. I would say that, okay, one of the reasons why we wanted to establish the benchmarks is that we realized one simple truth is that the better we sample from these tempered distributions doesn't mean that the metric we care about down the pipeline increases. So that's the same question about the beta, the same question like whether you need to sample from the product for like generating images or proteins, or do you want to quality of images or proteins? And these are kind of like, I would say, vaguely related. So that's a good question. Alternatively, the alternative to SMC, I see one is just like simply training the models that are aware of this, but I don't know like of any other good. Oh, I mean, of course, reduce, reuse, recycle by many people. You as well? No? Okay. It's like cluster of people are no and like will. And Yilan do. But yeah, the Metropolis has things correction on top. It's just like, maybe it makes more sense when we generate drugs, right? Like, because we just can throw any flops in silica, in silica, don't matter compared to the experimental thing. So, but once again, I think chasing the perfect sampling from the product is a little bit kind of like pursuing a different target. Yeah.
Thank you.
Yeah. All right, I think I'm over the time. Thank you so much for your attention.